0 when we expand it the other way, and therefore this is equal. In other words, we know a Markov process from x to y, etc., is Markov. Well, backwards, it's also Markov, y to x, and so on. So, the reason is that, yes, it's true, looking backwards in time, it's Markov, but it's no longer time-invariant Markov. Here, this is time-invariant Markov, going forward in time. But if we start with non-equilibrium distributions, we'll find, looking back earlier in the process, that this does not equal that. Yes, it's Markov. I only need to know things up to the most, the current state. But the transition matrix depends on where I am. So it's time-varying Markov going that way. It's time-invariant Markov going that way. So that would resolve the puzzle. Okay. In 1956, Kelly wrote a paper that related mutual information and gambling. And he came up with an optimal gambling on a horse race that would make your money go to infinity at the highest possible rate. There's something just a little bit the motivation just seemed a little special, a little off-kilter for this connection, and so it became a paper that wasn't much looked at or used. But it turns out to be the kernel idea for investment theory and for a number of other things. And it can be generalized to the stock market. So let's start on that. And the reason we're going to start on it is because if I have a good way to gamble on the next term in a sequence of text or music or some file, then I can essentially achieve the data compression associated with the log of that probability. And remember, the AEP says that you only need log 1 over p of xn bits to describe the sequence x1 through xn, and log of 1 over p of xn converges to the entropy, at least for IID random variables, and more generally. So gambling and what's called arithmetic coding, gambling leads to arithmetic coding, and arithmetic coding elicits the best gambling. So let's do pure gambling. We'll tie it together later. I'm going to gamble on a horse race, so I'm going to have horses. How many horses? Obviously, M horses. And probability of win. And those will be P of 1, P of 2, through P of M. And here, the P's are non-negative, and the sum of the P's are equal to 1. And I'll fly back and forth between the notation P sub I and P of I, depending on how explicit I want to be. All right, so we have the win probabilities of the horses. This means that one horse wins. The horse wins with probability PI, Nothing's left out. Then we have odds. When you go to the track, you find odds, and these are 4-1. I'll describe that in a moment. And this is O of 1 through O of M. And here the interpretation is bet of 1 on horse I pays back O of I if horse I wins. Let me flip a coin. Heads and tails. What are the odds? Well, there are actually two correct statements to make. One statement is they're even odds. The odds are 1 to 1. The probability of heads is equal to the probability of tails. If you and I contract that the winner gets $1, then 1 to 1 odds are fair. We first flip the coin. It comes up heads. Let's say you win. I give you my $1. If it's tails, you give me your $1. That's 1 to 1 odds. 1 to 1. At the racetrack, it works a little differently. They don't trust you. You say, I'm betting $1 on heads, and they say, let us see your $1, and I'll hold it. So they hold it until the coin flip occurs, and then they return your $1 and an extra $1 if you win, and they don't return anything if you don't. These are equivalent. But this says the odds are 2 for 1. At the racetrack, they're 1 to 1 if no one holds the other person's bet. So there's a short thing in the text that gives you, let's see, odds 4-1 are like 1 plus the odds 2-1 or something, you know, whatever we need to say to be correct there. Now, the reason they're odds 4-1, I think, I'm putting $1 out and investing in the horses, and then I get back a certain amount of money. And so putting the odds in the favor of 4-1, the way they are at the racetrack, is better than the equivalent way of talking about odds 2-1. All right. Now there are bets. And they would be B of 1, the amount bet on this horse, through B of M. Now here, we have a condition that B of I is non-negative. You can't bet more than you have on any horse. And the summation of B of I equals 1. We have 1 unit of wealth, whether it's dollars or euros or whatever, and it will result then in whatever this results in here. You say, well, why not equal A, the amount of wealth? Well, everything scales by A. So we'll just normalize it. It's a proportion of wealth that you invest in each of these events. Then the wealth S of X is equal to the amount bet on the X horse times the odds, the factor by which your bet is multiplied and given back to you with probability P of X. So what we've done is we've taken one unit of wealth and we've ended up with a random variable. Technically, 1 is a random variable, not a very interesting one. And that's essentially all that gambling is and all that investment is. It's the exchange of one random variable for another. Now the question is what random variable do you want here? Well, sadly, most people just content themselves with maximizing the expected value. So let's investigate that. Expected value of what happens when you invest B in the horse race is summation P of X with probability P of X. You bet B of X and return O of X. So P of X is the probability horse X wins. You get this payoff, and otherwise you don't. You get 0 back. And this is over X. Now this is not the way we're going to go, but if we pursued this, we'll maximize the expected value of S. Overall gambling schemes B. And you see that B is non-negative, it sums to 1. So the maximum this sum could take on is when you let B be 1, when the P of X, O of X is maximum. In short, all on one horse. B is all on one horse. All on one horse. The horse that X, which maximizes your expected payoff. All right, now, if you're Bill Gates, you take your $80 billion to the racetrack, and you say, very interesting. Here's a horse, the expected payoff of which is twice as much as I have. Now, I can turn $80 billion into $160 billion on the average. Expected value. So he said, who can refute this logic? So he bets it all on that horse. He loses. And then he's not Bill Gates anymore. So, what's wrong with this? Well, the fact is money compounds. It multiplies. You reinvest. And he's not allowing for reinvestment. He's assuming that you have a lot of small bets and that the expected value captures the sum of the outcomes because of the law of large numbers, and therefore that's all you need. Well, when this was applied to finance in the 50s by Markowitz, they ended up saying, well, you should bet all your money on the best stock. But everybody knew that was not a good idea. You wanted diversity. So how do you get diversity into this? Well, at that time, they looked at the covariance matrix induced by the portfolio B and essentially looked at the second moment, the volatility, or essentially the risk. So what you want is a high mean and a low variance.